The broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone. My name is Angel Francisco Martinez. I'm an application engineer at Midas, and we're coming at you from our office in New York live. Today will be the first of our two trainings for our tunnel series, for the Diamond Engineer Tunnel series, and we'll be having the second one next week, same day, same time. Today, we're going to focus on what we refer to as more of the pre-processing, and then we'll jump into a direct example as we're working on it. But basically, it means everything that is for preparing the tunnel and running the analysis. And then next week, we'll focus on some more advanced features, and then also on what we call the post-processing, which is the extraction of results. But the tool that we're going to be focused on today, GTSNX, or the software, has a lot of features for both. So we kind of want to break up the process as a simple, everything before on a simple example of a tunnel, almost like a static case. And then next week, we'll focus on some of the more advanced features for all the construction stage analysis that are more typical for a tunnel project, as well as the advanced features for extracting results. So briefly on an introduction, who we are, Midas as a company, we are the #1 developers of civil engineering software in the world. We also, as you might be aware, also do structural software, but one of our stronger software as well is Bridge, and as well as Geotech, as we're looking at today. Our headquarters is in Seoul, South Korea, but we're coming at you from our office in New York. And getting right into it on today's focus, which is, of course, tunnels, particularly tunnels on 3D. We're covering some of the main considerations that go into the design of these kind of projects. So, of course, starting off would be what kind of type, or the type of tunnel, or which basically means the shape is going to be determined, as well as, let's say, the reinforcement. And that, as we will see later on, can actually be done by different methods. Some even can do this by some hand calculations, and it's usually done by a structural engineer. However, as geotechs, we know that there's a lot more to consider going into a tunnel, and that's where we'll be seeing these other key points in the process. But everything from the basically sequence of construction, which comes down to the excavation method, has to be determined by the geotech engineer, and other local conditions, for example, what would be the water level or the pore pressure to be considered, if that needs to be improved, basically draining, what kind of status we have for our ground. Are we doing, excavating in soft soil or in rock, or is there stretches where we have a combination of both, as well as other things that only geotech engineers would really get a grasp on, like considering the pressure of the earth, the lateral pressure, and as well as if there's existing structures in place, how would this new excavation, this new project affect something that's nearby, adjacent, that's already in place. So all these, as you can imagine, is something that goes much more beyond what a structural engineer would typically be able to estimate or take into account in a more simplistic approach for designing the tunnel. So how do engineers typically go about this? As we're saying, if it was a very simple approach, there might be, even to get an initial estimate, you could do something even by hand if you wanted to. More likely than not, what you end up seeing is a structural engineer use some software where they simplify a lot of things and model the ground as simply as springs, and model everything else related to the earth and maybe some local conditions, even water, as pressure loads around the tunnel lining. And so from this simple approach, you can actually get some idea of what the demand is going to be, and hence you could potentially design as we said, shape the support system, including the thickness of what the lining would end up being. But it's, again, a very simplistic approach as to what's really happening in the ground. Whereas the next level beyond that is now actually considering the ground elements, either in 2D or in 3D, and that's really when you can get into beyond just what the support system more or less should look like, but what the pattern of excavation will be, especially once you hit 3D, as well as considering the nonlinear behavior of the local ground conditions that just cannot be done in springs. So, as geotechs, beyond just deciding the reinforcement of the tunnels, we have to consider the excavation method. These are the three main ones. I mean, there are of course more, but these, let's say, are the more common. The first being the open, cut, and cover method. It's probably the easiest to understand. Is whereas you basically have a deep excavation, you install your structure, and then you refill or cover the tunnel once it's in place. It has its advantages in the sense it's probably the most economical, but in urban areas, it's going to be the most disruptive, especially for traffic. And it requires the tunnel to be close to the surface. The other very common method would be the sequential excavation method, and popularly known as the NATM method, which is where you dig out the tunnel in stages, or as we said, in sequences. As we can kind of see here from the lateral view, you excavate parts and then reinforce, and then go back and excavate the other half of the tunnel section and then reinforce, and if you need an invert as such. This is a very well-established method. However, relative to other methods, like let's say the next one, the tunnel boring machine, it's much slower, as you can imagine. And it can be more economical, but you have to have a cost benefit between these two methods, and that comes down to basically how long the tunnel will be. So the tunnel boring machine is just basically, as we see in the image, just it cuts out the tube as it's going with these blades in the front, and in most cases the machine has its own system of installing the support panels as it's also going through. So it's almost automated completely. And this machine is great for what would be long tunnels. The only issue is that it's very capital intensive. It's very expensive to rent or buy the tunnel boring machine for the project. In reality, we see that projects have a combination of these methods. In a lot of cases, determining to the local conditions, you have part of the tunnel dug by one method, and then perhaps the rest of the tunnel or other parts of the tunnel by another. Again, this is something that the geotech has to also determine, the geotech engineer. But once they determine the type of tunnel and the excavation method, they have to go about the calculations. And the session of today is to kind of clarify or point out why tunnels in particular should be modeled in 3D FEM, or finite element method in 3D. So as we've seen, we could do some tunnels by just simplifying it, giving a spring and giving it some sort of stiffness approximation, but it's not really going to capture the behavior of the ground. That is more appropriately captured by what is known in the field as constitutive materials or constitutive theories. These numerical theories, they capture the nonlinear behavior of the soils, and not just capturing the proper behavior of the soils, but also once you start working in 3D, you can realistically have or you can accurately model the geometries of your structures, as well as all the loading conditions and all the other critical process of how these are interacting. And if you have complicated or more softer grounds, then you can even consider those initial conditions. The other thing is that once the project is ongoing, it's very clear that even the displacements, all the deformations, everything's going to be happening in the real side. It's going to be in 3 axes, and hence why to accurately represent and potentially capture areas of interest or critical areas, it has to be done in 3D. And so it's becoming more and more attractive to model in 3D. 2D, we'll see later, does have some benefits. It's still better than modeling from a structural point of view, which is just simplifying the soil as springs. But as we will see, there, especially depending on the geometry of the project, there's just simply things that cannot be simplified or captured in a 2D model. So everything we'll be looking at today will be in the GTSNX program, which is our platform for 3D finite element analysis. So the benefit, as I was saying, once you jump into a 3D realm, then you can get as detailed and creative, or as realistic as you want, and not just modeling the terrain, but also the structure with all its connections, any kind of reinforcement method or installation method. And if you have to consider existing structures in place as well. Now, while it might seem that working in 3D is a very complicated process, the point of the session today will be to show the typical workflow in our program, and just try to break it down into segments, into the following segments that, using our tools to set up or import the 3D terrain, and then using AutoCAD commands, or similar to AutoCAD commands, for generating the tunnels and the sections. We have a series of specific tools at every step of the process that verify that geometries are being properly represented and connected. It's easy to mesh, as well as verify the quality of the mesh. Easy to then, once you have the mesh, apply the boundary conditions and the loads, and then set up the analysis case to see the results. So we'll go through this whole process in an example of a simple tunnel. But as I mentioned earlier, we'll be focusing in this session in particular just a static case and how to obtain some basic results. And then next week's session, we'll focus more on the advanced features of construction stages and some of the methods that we have for extracting those results. Since for the most part, once you start modeling tunnels in 3D, you do start to get a high number of stages to consider, and that can get a little cumbersome to do manually. But as we will see next week, we have specific tools to also aid in that process. So let's jump into what we are referring to as the pre-process. So everything before running the analysis, starting with the modeling. And that's basically just comes down to you making a decision at the beginning of your project as to how you're going to capture the geometry. So we were saying you can go through this kind of decision process. Is there a way to idolize my geometry? Is there a way to simplify it? Can I capture it either in 2D or in an axisymmetric view? And if you can, by all means, it's recommended that you start off with something that can give you some initial estimates first. So we always suggest that you end up actually first doing a simplified version of your project in 2D, so you have a rough estimate of what to expect before you start investing a lot of time into the 3D model. But in some cases, or in a lot of cases, once you start to get into more advanced projects, it's very difficult to idolize the geometry, and hence why you have to go to a 3D realm, especially for complex. There's just intersections that cannot properly be captured in 2D, or if there's, as we were saying earlier, something already present that you have to consider, adjacent structures, or multiple tunnels in your model, or the ground layers themselves are not completely flat, which is almost never the case, then you start to really take a lot of these simplifications are becoming bigger and bigger assumptions. And so 2D has its benefits, and we really think it saves a lot of time to get some initial estimates, but it, as we will see, pays off to, once you have that, to go into the 3D realm for these kind of projects. So for our program, we will see we do have some benefits as to the modeling aspect. Part of it is that if you're familiar with AutoCAD, or even if you're not, the basic flow for this software, similar to ours, is that everything is icon-based commands. So you'll be able to click directly on any tab that's grouping those type of commands, and immediately identify under the icon the name of what the command does, and intuitively figure out what it is these commands are doing. Similarly, the program, as we were saying, has the versatility to allow you to work in 2D or 3D realm from the beginning, or even switch between. And other things that the program is great for is that it helps you stay organized by grouping everything for you automatically in what we call the work tree. And so you're able to immediately reach the point of interest, like your geometries or specific mesh sets or loads, or everything through the work tree to make changes. And lastly is our output window that gives you the message as to everything that you're doing as the analysis is running and all that. One of the main strengths of our program is the link, or the ability to link up and import any kind of AutoCAD file. So the most common types of AutoCAD files that we see imported, it would be for lines or DXF or DWG files, wireframe files. And we do have some general recommendations for before importing your file. So at the AutoCAD level, for instance, this example of these contour lines, we would recommend our user before importing to make sure that all the geometry or the type of line in AutoCAD is considered polyline. Also, very importantly, is that it's centered, that the coordinates of the geometry are close to 0, 0, 0. Basically, the origin would be here, to facilitate that the program can properly import this. And then beyond that, some details we do see a lot of times is that maybe if your drawing team is not necessarily the same person working on the model at the geotech level, he might just kind of draw some lines that look like they're intersecting, but once you zoom in, you see that there's actually a small gap, or it's not necessarily a smooth transition. So these little details is something that has to be cleaned up, and you want to make sure, ideally before you import, although you can also correct this once the geometry is in place. But these are the small things that sometimes there's an overlapped line. There's a line in the same spot, like two lines that visually only look like one. That would throw off part of not the import, but maybe once you try to start to mesh, you might be getting that there's some sort of duplicate geometry. So we also have tools to clean this up within the program, but these are general recommendations before you import. And the other important recommendation is that if your DXF file is composed of multiple lines connected, that you use the command explode before you import it from AutoCAD. So that just basically means that the lines are considered separate entities, not just one single one, so that it's properly imported. So that would be our recommendations for importing these type of files. However, the program is also very powerful in importing solid geometries, and here we have the list of the other formats that are common for our users to import. So what you end up doing is then, in a lot of cases, to save time, if your company has a team dedicated to drawing, is that you can just directly give them the specifications and just jump right into importing the shape of your tunnel, and it can be as detailed as you want it to be. And then you just focused about what the geotechs do, which is consider the ground, and combine the two. So assuming that you were able to get the CAD file, or you got the tunnel part down, the other aspect that we'll cover is how our tool is very easy, or has a lot of commands that are easy to generate the terrain, especially in 3D environment. So let's say to get to this point, we have a lot of different methods. We'll cover different ones, but one of the stronger ones that we have is this ability to take those contour lines and extract the surface, basically the topography, and also combine that with boring hole data that you can input manually by table format and giving coordinates of the locations, or you can actually just generate it in an Excel table, and the program would be able to read it and generate these surfaces automatically. And then from there, I'll show you in a second how you can then take those surfaces, divide a solid, and just retain the final geometry of your terrain by these simple tools. So looking at an easy example for this, I'll just show you this quick example. Let's say we have 5 boring holes and 1 topographic map. Here I'm importing a DXF file. This file is right now only polylines that show elevations. And additionally, we drew in 5 circles of where the boring hole data was located or taken relative to the surface. With a tool that we call bedding plane, I can specify by coordinate system, or as we will see here, the point of drawing these lines is that I can just click on them on the program, and then jump right into telling the program, at this depth, I have the first layer the next layer is at 70 meters, the third layer is at this distance, and then follow that in sequence until I have, in this case, the five boring log data, input it, and the program will then interpolate that into surfaces. So here now we see we've generated the 3 strata layers, or the surfaces that represent the strata layers, in a very easy table. And now we're gonna use our other tool called a terrain geometry maker to generate essentially a surface out of these elevations, these contour lines that we saw a second ago. So we're actually importing the same DXF file. And what this tool is, we can turn that DXF file into our topography. So there we're selecting the contour lines and we're giving it the dimensions of the surface that we're going to work on or we want to generate. And then the sampling points, the higher the sampling points, obviously the more accurate the representation. But you see that this tool then now has generated a surface out of these contour lines that I'm just going to then save in a format that can be brought back into the main model. Consider the terrain geometry maker as a subroutine or a subprogram. So now that I brought this back, we have these 4 surfaces. It's basically straightforward from here that I would generate some solid, in this case a block, that fits within the surfaces so that it can be properly divided. So in this case, I'm selecting the block to be divided in the 4 surfaces as what we refer to the tools. And then once the division has taken place, I can delete the top of the geometry that's not corresponding anymore. And we see here by changing the colors now, through these 2 tools, it becomes much easier to represent a 3D terrain in the software, as opposed to some other alternative might have been to draw some sort of 2D plane and then extrude it. But again, you start to make big assumptions about your surfaces being completely horizontal, which might work, in some cases for some simplistic approach, but most of the time it's a big assumption. So that's one way to generate the terrain. What we're going to do now is we're actually going to jump into the program and show you an alternative methods of doing this, one of which is to just import or generate a grid. And this grid can be, in this case, we're going to use our make face command. And we'll be using elevation data that's basically in a format, as I can show you over here, of just a notepad or a grid of elevations. So this represents one point elevation, and hence once you have those files, it's easy to create a full surface of this. So I'll open the program. Right now we're only focusing first on the geometry. Later we'll be getting into the meshing, and that implies also getting into the materials. But this is GTSNX. As we're seeing, the program has tabs that group all the commands together, as well as the worksheet with the little plus sign that expands to group everything together as well. So focus on the modeling, which is basically everything will be falling in the geometry tab. We will generate our surface for this example using the make face command here at the top left corner. And the options here, I would choose the grid face, which is the third option here. And I would specify here the size of my grid. So I'm telling it that my grid is a 50 by 50 grid. Here I would be telling it the location of where the grid would be. Again, recall this grid is basically it's a grid on the XY plane, but we're going to be then giving the information about elevations. And then lastly, we would tell it the dimensions of this grid. So I would be saying, even though I'm using 50 by 50 grid, I have to specify how wide in terms of the X and the Y direction this is going to be. So I'm going to make this the grid will be 50-50, and I'm just going to run this over a little bit past the origin. So I'm saying -1, -1 for the X and the Y. And I'm going to make the grid 202. So this become more clear in a second. And basically, I'm just ensuring that once I have my geometry in place for, let's say, the cube that we will be divided by these faces, that the cube falls completely inside. So here, as we said, I'm just going to select now the file that had the grid elevation information in this grid format. The program has this nice feature called preview that allows me to see how something's going to look before importing it. Up here, I can activate my axes. So we see here we have the first surface being generated out of this elevation data. And I would basically repeat the same process. The dimensions of the grid will stay the same, but this time I'm just going to upload the other file that I have. So I can do this repeatedly and generate the strata layers and the terrain or the surface through the same process as we're seeing here. And you can stack these as many as you need. So let's say for this simple example, we just have these two surfaces. One will be the terrain, and the other will be the one dividing the two main strata layers. As we saw in the previous example, what we would do from here then is generate some sort of solid geometry and then use these surfaces to divide it. So in this case, I will generate a cube that fits within these surfaces. And so my location will still be, at least for the origin, in the XY plane 0, 0, but now we'll make it for the C axis. I'm going to actually lower it by 20 meters, basically where the cube is going to start. And then here the dimensions will be 200 by 200, and this will be 220. So if you recall just a second ago, here I'm using the preview command. When we were importing the grid, we gave it an initial location of -1, -1. So what I was doing is I was basically just making sure that since the cube is going to be, this corner is 0, 0, I was just making sure that the surfaces on both ends will completely be sticking out. So here I'm looking at the top view, and it does look like at every point the surfaces are beyond or just beyond the cube. Obviously, this is something that you plan ahead of time, but even if I go to the right view or the front view, I want to be able to see that my surface is completely coming through the cube, or else I will not be able to divide. So the last inspection would be the front inspection, and I can see on both sides that the surfaces do pass. If the surface doesn't cut through the solid entirely, if there's a part of the solid that's not being crossed by the surface, then the program will not be able to divide it. So here we have now, even visually, you can see that the surfaces are sticking out. So we have what would be potentially now the final geometry of the terrain, and we would be able to now jump into the tunnel, in which case we're going to draw it using this command here. What we want to do though is, if we're drawing something in 2D in this case, we're going to draw first the 2D tunnel face, and then we'll extrude it. But when we're drawing a 2D face in a 3D environment, you could do it by coordinate system, but if you're trying to have some sort of visual guide as to, it's hard to tell on a white screen where the depth location is. What you could do, or you should use, is what we call the work grid. So right here is a command that turns this on. And that grid now gives you a plane on which to draw in a 3D environment. And you can move the work plane around by the different locations here in the workstream. But as we will actually see also next week, there's other ways to manipulate this grid over here called move the work plane beyond just the main axis and the origin. You can select any reference plane and then move it beyond that. But for now, actually, we are going to be working in the CX plane. I'm going to draw a tunnel to go in this direction. So I'm just going to put here now that I have the grid activated, I'm going to change my view to front view so that I can directly just draw on this face of the screen. So from here, I will then just go to what is here on the top left corner called tunnel, create tunnel section. In this command, there's a tab that allows you to choose the different shapes of the tunnel that you can draw. And if you want to include the invert in the drawing, let's just stick for now for the 3 center circle. And you can see the preview of it already here. which is located at the origin in the 0, 0 coordinate system for this plane. So then you start giving dimensions, and there is a guide in the program for the manual as to what that looks like. If we go to this part, you see here more or less what each of the radius corresponds to, radius 1 and radius 2, and what the angles correspond to. So I'm going to type in the values as I see here. R1 will be the radius of the main radius will be 15 meters. The second radius along the curvature will be 10, and these are degrees. And then we can also include the drawing of what is the distribution of the support system, the rock bolts in this case. So we will use 11 rock bolts that will be 7 meters long, and the pitch angle for these will be 5 meters, and that will give us this kind of distribution. And the last thing is basically to draw on the screen or just give the coordinate system of where the tunnel will be located on this plane, which is, remember, the CX plane that we're working on. So we're going to put it at 100 x. So we're going over 100, and then we're going up 20. So the angles actually here stay the same, 60, 55. This is, sorry, other way around. This is 15 and 20. R1 is 15 and R2 is 10. We see here now we're activating the rock bolts, and we can start to see the drawing. So we are going to keep it at 11 rock bolts, but we're going to make them 7 meters long. And here the pitch, as we said, is 5. And now what I will do is I can either try to find on this grid that point, which is, as we saw earlier in the screen, was 100 on the X and 20 on the C. Or I could have just typed it in. And I just click on it once to make that final drawing. From there, what we would do then is just take this 2D drawing and make a 3D shape out of it by extruding. So I am actually done with the grid, so I can deactivate it again up here by the work stream, right where the work stream meets the icon commands. There's a little icon for the grid. If I click on it, it'll hide it. And now I want to go here on my menu, top menu, look for the command extrude. And that command will allow me to, as we see here, select either a face, which is a surface, or a boundary, these edges, and generate a solid. So I'm going to extrude it in the Y direction, 200 meters. If we recall, that was the dimensions of the cube anyway, originally. And so that will generate my tunnel solid. We'll then have to divide it, but it'll give us the basic 3D shape. And then what I also need to do is use the command translate and essentially use the option to make copies of the rock bolts along the dimension of the tunnels that was extruded. And what we'll do is we'll generate 10 copies, each at 20 meters. So here I want to first extrude the tunnel. As it is now, if I try to capture, I'm not able to. And that has to do actually with this selection filter. The default for extruding something is to extrude the face. So I can either take one step and make a face out of this wire by just selecting the boundaries, making sure it's a closed boundary, like that. Or I can change the filter here and just tell it that I want you to make the solid out of these edges. They both give the same result. But just keep in mind that this filter is really handy for this selection process. So we'll just say we change the filter to edge. We'll select the boundary of the tunnel. I can then now move on to the next step here, which is waiting for me to tell it which direction. That's why this arrow is in red. But it's already confirmed to me with this check, this green check here, that this selection of the edges was done properly. And then from here, I would just give it once I select the direction, give it a distance. So we know that the length of this is 200 meters, but if I want to just kind of give it a quick visual inspection, again, preview is a really handy command. If I change my view to side view, I can see more or less how far I'm going. And we said the other thing we wanted to do is make copies of the rock bolts. So I'm going to use this command translate, and I want to select. I can try to select the rock bolts around the edge. It might actually just be so much faster if here in the work tree, I just go to the geometry tab and keep expanding the plus signs until I find my curbs, and just select all the curbs except, or actually wouldn't even matter if we include the tunnel section at this point. But let's just deactivate or deselect the tunnel section. So right now I have selected my 11 rock bolt geometries. I select the Y direction, and I'm not going to move it. I'm actually going to make copies, uniform copies. So that means that I am specifically telling it a distance and a number of times, in this case 20 meters 10 times. And if I preview it again, I can see the distribution. So we've generated our initial geometries, and we can now proceed into the process of combining all this together. So the first thing we would do is, like we saw in the previous video for the terrain, is once you have your block, you then use those surfaces to divide the solid and delete the extra part. So our divide command is here, right next to extrude. There's a solid divide. So the block would be the target solid, and the tools will be the surfaces that we imported. So I can either try to capture them directly from the model, or again, in the workstream, I have my two surfaces that I can just expand here. They're grouped together by type of shape. I can just select those two and preview it. If you do get a message saying that it's not possible to divide, again, it has to do with the surface geometry not completely crossing the solid. So here I can right click and go to delete part, or I can just click delete on my keyboard to delete this extra object. So we have the initial terrain created, and what we want to do now is go back and divide up our tunnel. For as of now, it's just a solid segment. So for that, I'm going to need my grid again. I'm going to reactivate the grid and go to the front view. With my mouse, I can zoom in, like with the mouse scroller. And this time, right next to where the tunnel drawing is on the top left, I'm going to go 2 over and select rectangle. What I want to do is, and I want to check this option here to make a face, is I want to generate a surface just big enough to cover what is the profile of the tunnel. If I hold the scroll button on my mouse down and move the mouse, I can then spin my model. So the grid is again no longer necessary. What I want to do now is I want to make copies of the surface all along. So that would basically mark the division of where the tunnel will be. So we go back to translate. As you recall, this is our command to move things, but also to make copies. And this time it's only the one surface. So again, I can select it from here, or I could have picked it from the workstream. The direction will be in the y-axis. If you can't see this, again, there's right next to the work grid, there's icon to show the main axis. Or as you're starting to see, the program has always an option to select from the workstream. So over here, there's the second option called datum. I could have also just selected the axis from here. And this time, we're going to keep the segments relatively long. So we're going to say every 50 meters 3 times. And if we preview it, this would be more or less the dimensions of where our division is. And we're keeping it very simple. As I mentioned, today's session is not going to be so much about a tunnel with many stages. That will be something we cover in the next session. Today's session will be more on the static aspect of it. Hence, we're keeping kind of the divisions in a very low number. So similar to what we did for the terrain, we now have to divide the tunnel by these surfaces. So I'm going to hide these two. I can either right click and say hide, or I can just deactivate from the box here in the work stream. And we're just going to go back to divide solid and use the surfaces. I'm going to click on the 3 surfaces to divide up the tunnel. This first surface wasn't selected because obviously it was just part of the initial geometry we needed to make the others. So potentially, if I activate my solids back, we could say, all right, we're done with the terrain. We're done with modeling the terrain, and we're done with modeling the tunnel and dividing it up. We would potentially be ready to mesh. What we want to do, though, is before we do that, is we want to double check that the program is aware about these geometries and how they're going to be in contact with each other. So we have a tool called check shape, or check duplicates, basically, that when you click apply, it'll highlight in orange the faces that the program recognizes are in contact. So as it looks in this example, the program recognizes that there's 2 soil layers, but it doesn't really recognize there's a tunnel inside. It only recognizes that there's divisions in the tunnel. So that being the case, we would need to correct that connection, and we have a command called autoconnect that would just allow us to select everything at the last stage and ensure, we can even double check again that now the tunnel is correctly being recognized here in orange. So this command is actually very, very important. I recommend that you get familiar with it. So in the geometry tab, you would go all the way to the right end under tools is the check duplicate command. So as we see it here, we see the lining of the tunnel is not in orange. So the program doesn't know that we want the tunnel to be considered almost as embedded in the solid of the terrain. So as we said, to correct that, right next to the bedding plane that we saw earlier today, there's an autoconnect command. And we would just choose the second option since we're working on solids. So now, if I go back to check duplicates, that issue has been corrected. The program will now, when we mesh, connect everything properly. So that takes us to the meshing aspect. Before we get into meshing, I'd like to kind of cover a little bit about the theory, or the theory behind how the materials are captured in finite elements, and that has to do with these numerical theories, constitutive models. And so they basically relate the relationship between stress and strain. And while the linear part, of course, is going to be similar for all of these different models, what we really start to see differential between all of them is the nonlinear behavior. And so, for some soil conditions, there might be hardening as you increase the stress. For some of them, there might be softening. So it all depends what your local condition is and what it is you're trying to capture. Either way, though, the process is as follows. You select a constitutive model to capture your behavior. You run in, let's say, the first analysis in your case, and then you verify. You inspect the results either by comparing them, ideally, if you have them, with field measurements. If you don't, then what you end up having to do is run what we call the back analysis, which basically all that means is that you run the same, everything about the model the same, but you start to vary some of the values either of the same material model or vary the constitutive model that you use. And then you run the analysis, an iteration process until you are having an idea, either by having a range, like an upper limit and a lower limit of the behavior you're more or less seeing. And then as you're going, once the project starts, as you're progressing through the project and you start to get field measurements, then you're again updating your model based on some of the field data that you have until you're much closer to what you're seeing in the field, and in that respect, calibrated your model. Here's a list of some of the main constitutive models that you can use for geotech in 3D. As we see on this list highlighted in red, let's say Hoke Brown and journalist Hoke Brown are very popular for the rock behavior, as well as joint rock mass. This would be more for transverse if there's different joints in opposing directions. If you're working on softer clays or softer grounds, there's the modified chem clay, there's the soft soil creep, there's hardening soil, small strain stiffness. Those are some of the more advanced numerical models for the softening or the hardening of these soils. Today, however, we'll focus on one of the more common ones, which is more column for the ground, and for the structures, we'll model the behavior as elastic. And then once you define the material, what you need to do is define how the material will be used in the program. So you would say from the element library, like, okay, so the rock will be a solid element, but the steel material that we define will be used as a truss, or the concrete material that we define will be used as a shell element for the lining. And depending on more advanced, projects, you might have to use interfaces or other things. But in the program, basically, for tunnels in 3D, your shotcrete support, your primary support system, will be modeled as a 2D shell element, although it can also be a solid. And then your secondary support, or your either rock bolts, will be your beam elements or your truss elements. And you can also have beam frames as well, or anchors, so that your 1D elements end up becoming, you can define the shape and use them for this. And then you define the thickness of your shell for the shotcrete. And then beyond that, once you're in 3D, you end up meshing with different methods, or we offer different methods for meshing. There would be either just selecting the geometry and using the auto mesh function, or there's the map mesh that gives you more control in the size of the elements, let's say in an axis of your choice. So you could potentially end up, let's say, meshing the face first and then extruding that mesh along a certain axis direction, and you have control over the spacing between them. The other features about GTS is we have options for the shape of the 3D element you want to choose between tetrahedral and hexahedral. They both have their benefits. This option for the hexahedral ends up being more efficient in terms of number of elements. It ends up having less number of overall elements than tetrahedral when you mesh let's say, the same geometry. What is good about our program is that you have other options for controlling to a very high degree the size of the mesh. So this one command we have is called size control. You can specify as either by spacing or number of divisions, but you can pre-specify a certain size of element near a specific area, let's say where the tunnel is, and then use a larger overall mesh size for the rest of the geometry. And the program will do that gradual transition for you so that you don't lose quality in the results, but you don't have a heavy uniform size mesh for the rest of the model, which it just means it takes longer to compute. So let's go back to meshing quickly our 3D model. We're just going to use a uniform size of 8, and we'll stick to the default, which is tetra. So here, I will now go to the next tab, which is mesh. Here is where the materials will be defined. In this case, for the starting file, we have our 2 layers. If you wanted to create a new one, you basically just go here to create, and you would select your constitutive model. And as I mentioned, what's going to vary between them is the nonlinear tab, the nonlinear behavior. And then once you define the material, you would tell the program how it's going to be used. This material will be for a 3D solid. This other material will be for a 1D truss, etc. And then you would just go to mesh, which is right here in generate 3D mesh. We'll give this a value of 8. And this first one is the soil, the top layer. You could also mesh these in what would be, let's say for this part for the tunnels, they all have the same material. I can just select the rest of the geometries, assign the same material, and this will basically be meshing in parallel. So it meshes them all at the same time. And now I would just have to, in my work tree, kind of modify the name. So I know that that's the rock, but just kind of clarify to the program, all right, this would be, let's say, here in the property window, tunnel 1, etc. So I could have meshed these, in stages, but the alternative is doing this way. Just mesh it all together if it has the same material, and then just make sure that in the work tree, you just go back and specify, especially if it was important for sequences, which is the order in the name that you're going to be working these out. From here, what I need to do now is get the lining of the tunnel, which, as we were saying, it's a 2D shell. So we have a command called extract that, since we already meshed the inside of the tunnel, I don't have to specify a size of element or a type of element. The program will just make sure that everything is connected, but generate a 2D surface with my structural property that will end up becoming the lining. And I can do this by selecting the nodes from the mesh tunnel, or I can just select the geometry, the original geometry, which is much faster. So here I'm going back to the work tree, activate everything, extract command this all the way to the right element, extract. And the type, I'm just going to select face. Here is where we have the material defined. This is the lining. And I would just give the command OK. And so that when I turn off the geometries, well, we see here that the lining was generated as a single system. So I'm actually going to undo this, just because what we really want to do is that each section has its own separate mesh created. So I'll go back to extract, face, and again, I select everything, but now this is the option where you tell it register everything on its own. And I actually also want to say not to create a face in between the tunnels, just on the outside boundary. So we see there now with this option, there's the segments already created for me. However, the outer boundary for the front and end of the tunnels have also been generated. So I just have to delete that real quick. I'm going to put here the side view. And in this, where we were selecting the filter between face and edge, there's now other options. So I want to go now to element and just draw a simple rectangle on both ends. By not going too far in, I'm ensuring that I'm only capturing the faces. So that now when I press delete on my keyboard, we see that I've retained the outer boundary only. And then now the last thing would be to generate the 1D elements, which are the rock bolts. I will give them 3 divisions. So one node, or this line will be divided into 3. Here's where I selected the material. And in this case, I can hide the meshes just to show you these. I can select all of them. Doesn't really matter that the first tunnel boundary is also being, in this case, meshed as a rock bolt, because what I end up doing is just deleting the first and the last one. I'm just going to click delete on my keyboard. And we've now retained basically all the behavior that we wanted to in terms of elements. So we just did here. And from here, well, the process is simple. Similar to is varying the type of material, you can also run several iterations by just creating multiple thicknesses of your shell and running the same model, but every different analysis case, just using a different thickness of property until you get to the point where you're sure that it's supporting the stresses that it has to, or it's minimizing the displacements to the acceptable level. So this is how the geotech engineer, through iteration process, can determine the proper thickness of your lining. We have tools. We saw the tool earlier about generating and checking the geometry connection. We also have one like that for post mesh. After you mesh, you can check and make sure that the free faces check is that you only see the outside boundary. If I can see the inside of my tunnel like I have here, then that means that it's not properly connected. So in quick inspection to our model, it's right here under check. it would be the third option called free faces. And we see that I only see the outer boundary, so my model is properly connected. Oh, sorry. We do have the option to also have interfaces. If you needed to model some sort of a big fault in your model, you can define the stiffness or the friction between the layers and model this as a plane interface. But once you get past all the meshing, then you would be now moving on to applying boundary conditions. There's different kinds of boundary conditions specific to consolidation or seismic analysis. In our case, we're just going to do the normal constraints of our boundary. We'll use the auto feature, and we'll define the water level. We'll see next week that for tunnels, what you also have the option of doing is instead of having to mesh two different materials into one shape, you can just start with one material and tell it that eventually that material is going to change at a later stage. So, for example, first this tunnel boring is being excavated, and then later it's activated as a support segment with concrete in the process. So here I'm now ready to go to the next tab. And here's where the boundary is, constraints, auto, and I will just click OK. So the reason we use the cube shape in the beginning is that the program will recognize those boundaries and fix the degrees of freedom accordingly. I will now define the water level. So we can do this as a global water level, but if we have a, say, particular surface that we want to use as a guide, we can select that directly on the geometry. And then we just activate it in the control, analysis control. So this is what I was referring to earlier about the change in the properties. Initially, the part of the segment is just rock and it's excavated and then reactivated with a different material. And then for loads, we have many different kinds of loads. You can apply forces, pressures, prescribed displacements, moments, even beam loads that you can apply if you're only modeling the tunnel as a support, beam, and a very simplistic approach. Temperature loads, initial stress loads. Well, in this example, we'll just end up applying self-weight, the gravity load, but we'll see examples next week about applying some of these other pressure loads. So here we just go now to self-weight. This is just gravity. And the model will basically be, let's assume in this simple example, ready to run the analysis. So you can run all these kinds of analysis in the program: static, slope, stability, dynamics, some sort of seepage coupled with stress, settlement or consolidation analysis, and of course construction stages. As I said, this becomes very advanced for tunnels because you can get hundreds and hundreds of stages. So we'll focus for the tools for this next week. Today, just because we're finishing the session up, we'll just do a very simple static analysis. So all we'll do basically is look at, let's say, the finals, or if the tunnel was already excavated, and we'll only have deactivated the support systems and the soil, but the inside or the tunnel segments were already taken out. And then we'll see here in the analysis control is where you can turn the water pressure into a load automatically, and specify other initial conditions, including the K0 condition, the level or pressure, and then just run the analysis. So we would go to the analysis tab at close to the end on the right, here in general. Here's where you select the type of analysis you're running. For now, we're just going to select the second option, which is nonlinear. It's not a bad rule of thumb to first just run a simple static analysis before you define many, many stages. Here what I'm doing is you can drag and drop. As we said, the tunnel segment, we're not simulating the excavation. We're just going to assume everything's already been excavated, and I'm just activating my loads and boundary conditions. And here's where you would just, in the analysis control, tell the program, I want to have these initial stresses as well considered. And this is where you can define your water level. You would select it here from the from the table if you had selected a particular shape, or you can just give it a global size. Since we specified a shape, I'm going to give this a value of 1. I'm just basically, this turns into a multiplier to where this water level is. This is one part where you have to be a little careful with the units. Just make sure that you're keeping track. The water level might be higher or lower if you're switching between meters and feet or such in between. And then we would just run the model. We would go here to perform and run the case. Here's a little more details about some of these initial stress conditions and the water levels, if you want to consider saturation effects. So there's very advanced considerations that you can control in the program. But once you run the analysis, you end up now joining or getting into the results, which is what we call the post processor. And so for this simple case where we'll just inspect something like the displacements and maybe some axial forces on the truss or moments on the lining. But we're looking at, again, at a very static case, or we're looking at the static case, not the process of construction, which we would have to specify manually. But the program gives you both ground results and structural results, and it's grouping them, as we see over here, by type of result, but you also see there's a name by the type of element in front. So if I wanted to see the axial forces, I would expand the truss tab. If I wanted to see the lining, I would expand the shell. Everything else would just be under the normal 3D. And once you've set up this model, actually, you could run the same model under different types of analysis. We can run a slope stability analysis for this shape, or depending on the boundary conditions and special loads, we could also run dynamic analysis, moving load analysis, or as we mentioned, very important for tunnels, and the focus of next week's session will be, once you start to get into the construction stages, you'll see that for 3D tunnels, this easily becomes many stages. And so we have to find tools, or we have tools to allow us to simplify this process as well. Because as you'll see, this same model, if I was to run it even in just 4 excavation stages, the results would look quite differently. The concentration is now more about the process of the installation itself of the tunnel, not just a static case of how much potentially it would be affecting the whole slope. And beyond that, with our program, if you have like a bridge or structural software, you can import the structure and potentially see how a new tunnel excavation would affect an existing structure. And you can get both results for, the bridge team could also be working with the geo team directly and get results for the piles and the structure as well as for the tunnel. So I'll go back to the model, but I'll finish the presentation slide here. So overall, conventional methods are very practical. I think they serve a very important process or purpose in the beginning to have some initial estimates. But beyond that, you have to realize that there's a lot of simplifications. You're taking a lot of assumptions done. 2D is a step forward. There's definitely, at least you're capturing the ground in your analysis, and you can have some nonlinear behavior up the ground. But again, the assumption is that it's a segment, and the shape is going to be very simple. Like the ground will probably be completely flat, and the tunnel is symmetrical or is supposed to be straight. But then, beyond that, it's also good to run a 2D analysis first, see if your materials are making sense. If something is deforming too much, it could be a value in your soil. You can even start the calibration process in the 2D to make it faster. But then once you have your final or your initial estimates, jumping into 3D, as we saw, it's the most accurate way to represent not just the terrain, but also the process, the construction process. But this is also an iterative process. You have to go through several runs and calibrate the model as you're going through it. So our analysis here finished running. This is the message we get at the output window if there's any warnings and seconds. As we saw, now we're in the post mode, and if I go here to my results tab and I expand, this is where the different results are. As we said, we can see specific to the type of element. We can kind of slide this down. But you would see that once we get into construction stage analysis, each stage would have its own tab, and you could see the progress. But again, all that will be, all the different kinds of extractions of results will be covered in the next session. We do want to say that for some of you, if you want to try this out, we have a very simple example that we're about to immediately, when the session is over, send an email to all the participants. We'll include the model files and this example as well. This is a tutorial that we have, but we simplified it for those of you who want to try it. The star file will have already the material defined. It's only going to be a beam. It's only modeling the lining. In the ground is modeled as springs. And the process will be, you get to practice is drawing the tunnel, meshing the 1D tunnel, applying the loads, the beam loads, defining in this case, the boundary condition, which is represented by springs, and then just running the analysis. We'll include these slides that will give you all the specifics for the dimensions of the tunnel, what size of mesh to give, and then the distribution of the loads. What I do want to point out here is for this particular load, you first specify the starting point, the ending point, and then you select the objects. And as you see here, because of the positive versus negative in terms of values, that's what determines if the load is being applied to the left or to the right. So for the lateral pressure load in this case, on the left positive, and on the right it's negative, and that's what makes these loads be applied in those directions. And then for the vertical, we'll do the self-weight, and then the vertical load is also applied by halves, but only to the middle. The boundary condition is we, for stability, constrain the top node in the basically horizontal movement in the X direction. So it can sink, but it won't go left or right. And the ground is applied as a surface spring. So you go to create, other, and you select the option surface spring. And here's the calculation of how we determine, what the subgrade modulus of subgrade reaction is. Basically, you're defining the soil as a spring. And then you just be able to run the analysis as a static analysis with all the loads activated. So for you, if you want to try it, you can create the model and then send us a screenshot of one of these results, and we'll count that towards a certification of using the program. So you would be able to email it to us here if you like. The other thing I want to point out is in our website, we will be uploading under review courses the recording of the session, and you would be able to also directly from our website download the material. But as I said, we'll be emailing it to everybody who came to the session as well. But that's basically the conclusion of this initial training. If you have questions, we can answer them now, or you can send them to this email or this website as well.